Welcome friends. In the last video I uploaded for the formation of partial differential equations. In forming the partial differential equation there are two types we have discussed. First type is by eliminating arbitrary constants from the given equation, and second one is by eliminating arbitrary functions. Now, before again starting with the formation of eliminating arbitrary constants, in this throughout this module we are using z as a function of f of xy, and we are using usual notations as dou z by dou x is equal to p or zx, dou z by dou y equal to q or zy, and second order partial derivatives dou square z by dou x square equal to r or zxx, dou square z by dou x dou y or dou square z by dou y dou x are one and the same. It is denoted by s, that is equal to zxy or zyx, and another one dou square z by dou y square equal to t, that is zyy. p, q, r, s and t we are using. Now some examples on forming the partial differential equation by eliminating arbitrary constants we'll discuss here. Let us form the partial differential equation PDE for the family of all spheres whose center is on z equal to 0 plane. That is important. Z equal to 0 plane and having the radius r equal to constants. Here we know that the equation of the sphere whose center at ABC and having radius r is given by x minus a the whole square plus y minus b the whole square plus z minus c the whole square equal to r square. Here ABC is the center anywhere in the sphere. Okay, but in this particular problem they given as center lies on the z plane, z equal to 0 plane. If z equal to 0 plane, on that plane the z coordinate c will be 0, the center c will be 0 for that. Therefore the center lies on the z plane, that is the z coordinate is 0, then a b comma 0 will become our center. Therefore equation of sphere is given by x minus a the whole square plus y minus b the whole square plus z square equal to r square. This is our equation of a sphere. Here a and b are arbitrary constants and r is our absolute constant. We may eliminate r square or it may remain in the equation itself. But to form the partial differential equation for this equation of sphere, let us differentiate partially with respect to x and y respectively. If we differentiate partially with respect to x, here x minus a the whole square, by using chain rule 2 times x minus a into differentiation of x minus a will become 1. Whereas differentiation of y minus b the whole square with respect to x will become 0, and differentiation of z square is 2z into dou z by dou x, that is equal to 0. Now simplifying, 2 cancels. If you shift to the other side, then 2 cancels. X minus a is equal to minus z into dou z by dou x is p. And in the second part, partial differentiation with respect to y will become x minus a the whole square will become 0. Differentiation of y minus b the whole square is 2 times y minus b into differentiation of y minus b will become 1 into z square differentiation is 2z into dou z by dou y. Here we are differentiating partial with respect to y. Simplifying this, shifting to the other side, y minus b equal to minus z into q. Then here x minus a I know and y minus b I know. If you substitute in the given differential equation, given equation of sphere, we'll get z minus minus of minus of z into p the whole square minus z into q the whole square plus z square equal to r square. Then taking z square common, and due to square negative sign will eliminate, that is taking z square common, p square plus q square plus 1 equal to r square. This is your required PDE. Here r is absolute constant, that's why we are not eliminating this. In another example containing log, I will solve here. If z is equal to a into log of x square plus y square equal to b is the given equation. For this, what is our partial differential equation? Again, a and b are arbitrary constants. I have to eliminate a and b here. Differentiating partial with respect to x, dou z by dou x will become p, and a is constant. Differential of log of x square plus y square is a chain rule, considering this one as x 1 divided by x square plus y square, and differentiating x square plus y square with respect to x again. Differential of x square will become 2x. Differential of y square is 0, because we are differentiating partially with respect to x here, and differential of b is 0. Therefore, p equal to, I can write it as 2ax divided by x square plus y square. Like that, while differentiating partially with respect to p, with respect to y, dou z by dou y is written by q, and a into, again chain rule, 1 divided by x square plus y square into differential of x square plus y square with respect to y will become 0 plus 2y. Therefore, q is equal to 2ay divided by x square plus y square. Now I can solve for a here and substitute, but what happens? Again b will remain. That's why in forming the partial differential equation, after finding the partial derivatives, we can do any operation, addition, multiplication, or multiplying something to the one equation, and adding and subtracting can be done. But a and b should be eliminated, that is arbitrary constant should be eliminated. In this simple way, how to find the partial, how to eliminate this a from this is dividing p by q. Then automatically our a will eliminate, p divided by q. P is 2ax divided by x square plus y square. Q will be reciprocated, x square plus y square divided by 2ay. 2a cancels, x square plus y square also cancels. Therefore, p by q is equal to x by y. Cross multiplying, py equal to qx, that is py minus qx equal to 0 is our required PDE. Okay. Now, similarly, two more examples I would like to explain here. Form the PDE from z is equal to log of b into y minus 1 divided by 1 minus x. Again here to eliminate a and b. To eliminate again constants, we are going for the partial differentiation. While taking the partial derivatives, you have to apply the chain rule here, and then quotient rule and all those things. To avoid that, let us use the properties of log. We have the log properties as log of m into n is equal to log of m plus log n, and log of m divided by n is equal to log of m minus log n. Using those properties here, I can write the given expression as z is equal to a into log of b into y minus 1, m into n. I can write it as log b plus log of y minus 1 divided by 1 minus x is there. Therefore, m by n, log m, total m minus log n. Now it is very simple to differentiate. Therefore, differentiating one partially with respect to x, dou z by dou x will become p equal to a into log b constant 0. Differential of log y minus y also 0, because we are differentiating partially with respect to x. Therefore, differential of log of 1 minus x is 1 divided by 1 minus x into differential of 1 minus x will become 0. Differential of minus x is minus 1. After simplifying, P is equal to A minus of minus plus A divided by 1 minus x. Similarly, partial differential with respect to y, Q is equal to A into 0, 1 divided by y minus 1 into differential of y minus 1 will become 1 minus 0. This is totally 0. Log of 1 minus x. Differential is 0. Q is equal to A divided by 1 minus. Again, I have to eliminate A here. In spite of substituting in a given equation, I will divide P divided by Q. P divided by Q, that is A divided by 1 minus x into reciprocal of the Q, y minus 1 divided by A cancels. Therefore, y minus 1 divided by 1 minus x. Cross multiplying 1 minus x into P equal to y minus 1 into Q, or simplified form equal to, this is our required PDE. Up to these, whatever the examples were solved are containing only P and Q, that is first order partial differential equations. If the differential equation is containing number of arbitrary constants more than the number of independent variables, then the differential equation is of a second order. Differentiating with respect to x, I'll get differential of x square is 2x divided by a square, differential of y square is 0, and z square differential is 2z divided by c square into dou z by dou x, because z is a function of x. Simplifying this, shifting this to the other side, minus z divided by c square into dou z by dou, 2 cancels. Simplifying this, c square is shifted to the other side, minus c square by a square equal to z into this 1 by x, I'll write other side, into dou z by dou x. Differentiating again, here it is not possible to eliminate c square by a square. Therefore, differentiating again with respect to x, I am going to get right hand, left hand side as 0, and taking the three terms, then z into differential of z into 1 by x as it is, differentiation of dou z by dou x will become dou square z by dou x square, plus z into dou z by dou x as it is, differential of 1 by x is minus 1 by x square, 1 by x into dou z by dou x as it is, differential of z will become dou z by dou x again, which is equal to, again taking LCM as x square, here only one x is there, therefore multiply by x, and here x square LCM, and no x term is there, multiply x again, it will come. Therefore, x square is shifted to the other side, zx into dou square z by dou x square is replaced by r, dou z by dou x is replaced by p, dou z by dou x the whole square is replaced by p square. This is the required second order partial differential equation. R is coming dou square z by dou x square. Therefore, it is a second order partial differential equation. Thank you.